Okay, so in this video we're going to start to talk about synapses. If you remember in the last video we talked about action potentials. We talked about how the sodium and potassium exchanged to send this electrical signal down to the axon terminal. So what we're going to look at today is what happens when that action potential does reach the end of the axon, and how do we stimulate, and what are the possible different stimulations of this, what we're going to call post-synaptic structure. So when we look at the synapse, we've got the presynaptic neuron, so the neuron that we've been talking about, and that's going to consist of an axon terminal, the end of the axon, which is going to contain a neurotransmitter. And so we've kind of just indicated with our blue dots that we have a neurotransmitter within this. We call them synaptic vesicles, this little chemical-filled pouches here, if you will. Notice on the outside of that axon terminal, we're going to have larger amounts of calcium. So we've got a concentration gradient for calcium, just like we did for sodium and potassium within the axon. And then on the other side of the synapse, we have the postsynaptic structure. So we just kind of outlined it here as a box. That could be a muscle, skeletal muscle, smooth muscle, cardiac muscle. It could be a gland, or for our purposes in this lecture, we're going to say that it's a dendrite. It's a receiving area of what we could think of as neuron number 2. So in this case, we have neuron number 1 that's going to affect neuron number 2. And we're going to talk about different ways that we might be able to affect this thing. So notice, when we look at this synapse, there is going to be a gap. This is a physical space that we call a cleft. So the synaptic cleft is a gap that we're going to have to bridge. Now, if we think about this, axon number 1, we have an electrical signal being transmitted. We're going to continue with an electrical signal in the postsynaptic structure, whether it's a neuron or skeletal muscle depolarizing, whatever it is. So somehow I have to bridge this gap. I'm electrical, but I'm separated by a space. And that electrical current cannot jump that space. We have to use something else to bridge the gap. And so what do we use in the body? A chemical neurotransmitter. Now, this neurotransmitter, we'll see, is going to be released across the space, and it's going to cause something to happen over here in the postsynaptic structure. This is going to be the slowest part of the transmission. And so the chemical neurotransmitter is not as fast as the depolarization, repolarization, the action potential electrical current. So the more synapses we put in a nerve progression, the slower the overall transmission is going to be. It's kind of like saying you're driving your car, you get to a river, and you would like to drive your car on the other side of the river, but we don't have a bridge. How are we going to get across the river? Well, maybe it's a ferry or something like that. Obviously, driving a ferry across is going to be much slower than the speed you are driving your car on either side of this river. So synapse, chemical transmission, is going to slow us down a little bit. Now, how does it happen? Well, action potential comes down. We're talking about changing membrane voltages. So calcium is going to have a voltage-regulated gate. It has an electrical charge, just like sodium and potassium did. And when calcium is allowed to enter the cell, calcium binding to these little synaptic vesicles is going to cause the release of the neurotransmitter into the space. Now remember, we talked earlier in the semester, when we talk about chemicals having an effect on a structure, we said that there has to be protein receptors on that postsynaptic structure specific to the neurotransmitter. It's the interaction of the chemical neurotransmitter and our receptor protein that's going to cause something to happen. Now, this postsynaptic structure, we're saying it has sodium on the outside, it has potassium on the inside, just like we had in our axon. It also has a resting membrane potential. So let's say that our resting membrane potential of this structure is negative 70 millivolts. Same thing that we used on the other side. If the presence of my neurotransmitter opens sodium gates and allows sodium to come in, sodium is going to enter the cell. What are we doing to the inside of the cell if we add this positively charged sodium? Are we making it more negative or less negative? Less negative. We are depolarizing. So the question is, if you think of action potentials, we somehow went from negative 70 millivolts to negative 55 millivolts. We said that was our threshold. Well, how did we hit that threshold? A chemical neurotransmitter allowed sodium gates to open, allowed sodium to leak in, and got us to that threshold so that now we open the voltage gates and we allow what we would think of as depolarization. This is the trigger. That neurotransmitter is dictating what is going to happen in this by causing sodium gates to open. We refer to this as an excitatory postsynaptic potential, or EPSP. It's an excitatory postsynaptic potential because we're exciting the structure after the synapse. And so sodium coming in, allowing us to hit threshold, is going to continue the signal down that second neuron. If we were talking about skeletal muscle, we would be talking about the skeletal muscle contracting. If we were talking about a gland, we would be talking about the gland releasing its product. Excitatory. Sodium coming in, causing that second structure to fire. Now, the other thing that could potentially happen, remember, sodium on the outside, potassium on the inside. What if I had a different neurotransmitter? What if I had a neurotransmitter that, we'll give it its own receptor proteins because it's a different one, but what if the presence of my neurotransmitter did not open sodium gates? What if my neurotransmitter opens potassium gates and allowed potassium to leave? What would I be doing to this resting membrane potential? Am I making this less negative or more negative? Well, I'm eliminating positive. So in this case, I'm going to become even more negative because I'm allowing potassium to leave. We would refer to this as hyperpolarization. I'm moving even more negative. I'm moving away from my threshold. I'm becoming more polar. So the question is, if this is becoming more polar, if I've hyperpolarized, is this secondary structure going to send a signal? Did I hit threshold? Well, we said threshold's negative 55. I just created an event that took me from negative 70 to negative 100. Did I hit threshold? No, I moved the opposite direction. And so, in this case, this structure is not going to fire. This thing has been inhibited. It's been blocked. So, did we excite it? No, we did not. This is an inhibitory postsynaptic potential, or an IPSP. In this case, my second structure, if it's another neuron, is not going to fire. So that seems kind of weird. Why would we send a nerve impulse that gets to the end and does not cause the second structure to fire? We've blocked it. Well, it sounds weird, but it's normal. Inhibitory postsynaptic potentials happen all the time. And I want you to think of muscle contraction again. Let's go back to some of the stuff that we talked about with agonists and antagonists. Again, with movement, we said we just decide where we want to be in space. We don't worry about what muscles are contracting and what muscles are relaxed. So let's say that you want to get a drink of water, or you want to scratch your nose. I'm going to bring my hand to my face. Who's the agonist? Who do we want to contract? The bicep muscle brachialis. Well, we said the antagonist is the triceps. So if my goal is to bring my hand to my face, what do we want the antagonist muscle to do? We want it to relax. We want smooth, continuous movement. So while the agonist is firing to allow us to move, the antagonist is being inhibited. So, hand to the face, I'm exciting the bicep muscle and the brachialis. I'm inhibiting the triceps. I don't want that muscle to fire. And again, we don't think about that. That happens automatically. All we decide is where do we want to be in space, and the brain takes care of everything else for us. So again, think of that patient with Parkinson's disease that maybe has rigidity when they move. Why? Because their agonist pathways are excited, but they're losing the ability to inhibit those antagonistic pathways. And now I've got two opposing muscles fighting over control of a movement pattern or over a joint. So inhibitory is normal. We see it a lot with eye movement, for example. So a normal process. And then the last thing that we'll mention, put some new numbers up here. Numbers that we already talked about. We said a resting membrane potential of -70, a threshold of -55. Go back to our excitatory potential for a second. What if we allowed a little bit of sodium to come in? Enough sodium to get us to, let's say, -60 millivolts. Did this thing fire? Did I reach threshold? No. I've got to get to -55 for those voltage gates to open. If I don't reach that threshold, they're not going to open. But am I closer? Yeah, I was 15 spots away, 70 to 55. Now I'm only 5. I'm closer because I allowed some sodium in. So if I could get a potential from another source, another axon terminal releasing neurotransmitter, that might be enough of a boost to allow me to excite and send that signal. The last thing I want to mention about this, because I didn't say it before, if we're thinking about a dendrite in this postsynaptic structure, these gates for sodium and potassium are chemical gates. They are opening in response to the presence of a specific chemical, a neurotransmitter. And so some of these neurotransmitters will be excitatory, and a lot of the neurotransmitters in the brain are actually inhibitory. They prevent a process from occurring. So I can, at the synapse, I can excite and continue the nerve impulse. I can inhibit and block that impulse, or I could facilitate and bring myself closer to threshold But again, I still got to have a little extra bump. I need still a little more neurotransmitter, maybe from another neuron source, to get me over the hump and allow that nerve impulse to continue. All right? So that's synapses. That's a little bit of these postsynaptic potentials and what's going on there. And that brings us kind of to the end of our chapter 11 information. So I hope that supplements your notes, and hope that helps. So we will talk soon. Thanks.